Hello there, Mr. Sutton here, bringing you the IM3 Chapter 8 Quiz 2 Extra Practice Solutions on Probability. For this one, we randomly pick a marble out of a bag with 5 purple, 9 red, 3 orange, and 16 black marbles, and we want the probability of a marble that is not red. So to make my life a little bit easier, since we've got all these different marbles, I think it might be simpler just to find the probability of a marble that is red and then subtract it from the total. So let's see here. We've got a total of, and again, I'm finding probability of red first now, not red. So this isn't directly answering the question, but I'll get there. So we have a total of, let's see, 5 plus 9 is 14, plus another 3 is 17, plus 16 is 33. So it's going to be something out of 33. Now, how many red marbles were there? There were 9. So 9 out of 33. That's my chances of red. And while I'm at it, I have a choice, but I'm choosing to reduce this now to 3 over 11. Otherwise, I'll have to reduce it later on, and hey, whatever. We're here now. So now I'm actually going to find the probability that my marble is not red. To do this, I just have to subtract the probability that it is red from 1, basically subtracting this percentage from 100%. So 1 minus 3 elevenths ends up giving us 8 elevenths. And 8 elevenths is the probability of picking a marble that is not red. On this problem, we're drawing a card out of a standard deck, which remember has 52 cards. We want the probability the card is not a face card. So I'm going to do this by figuring out the probability that it is a face card, and then I'm going to subtract that from 1 to get the complement. So figure out the probability that something doesn't happen, and then subtract it from 1. A little bit faster than counting up all the times that we don't have a face card. All right, so probability of a face card. If we have a standard deck, there's 52 cards overall, so this is going to be something over 52. And the face cards, remember, those are the jacks, kings, and queens, jacks, queens, and kings, of which there are 4 different varieties of them because there's 4 different suits. So that's a total of 12 of those face cards. And if you want to, you can reduce it now. You'll have to do it later if you don't. So that reduces by 4s to be 3 over 13. So now the probability of not getting a face card is just going to be 1 minus the probability that we do get a face card. So 1 minus 3 over 13. This could be rewritten as 13 over 13. So then subtracting that, we get 10 over 13. For this problem, we flip a coin 60 times. 32 times we get heads. And for the first part, we want the theoretical probability of flipping heads. So this is just saying, based on the experiment, how many times would you expect to get heads? So it's basically desired outcomes divided by total possible outcomes. So there's 2 outcomes if you flip a coin, heads or tails. And out of those, only 1 is what we want here, heads. So our probability then is 1 out of 2. Now for the experimental probability, we're basically asking how many successes did we get out of how many times we actually tried. So this is based off of what actually happened. We have a total number of tries of 60. That's our total possible outcomes, essentially. And we're going to divide by that, we're going to divide the number of successes, which was the number of times we flipped heads here, 32 times. And then we can reduce that by, let's see here, 4s to be 8 over 15. For this problem, we flip or roll a 6-sided die 40 times. A 3 is rolled 15 times, and we want to compare the theoretical and experimental probability of rolling a 3. So the theoretical probability, that's just the number of desirable outcomes divided by possible outcomes. When you roll a die, there's 6 outcomes you could get, and only one of them is what we're looking for. Only one of them is a 3. So our theoretical probability of rolling a 3 is just 1 out of 6. But now when we actually did this 40 times, we got a 3 15 times. So our experimental probability is going to be the number of successes over the number of tries that actually happened. So for our total number of possible outcomes, we use the number of tries, which was 40. And for the desirable outcomes, we use the successes, which was 15 times that we rolled a 3. So 15 out of 40 is our experimental probability. And we could reduce this by 5s to be 3 over 8. For this set of problems, we need to figure out if the events are independent or dependent and find the probability. So these particular problems, we have a small bag with 6 pennies, 5 nickels, 3 dimes, 5 quarters, and 2 $1 coins. And we choose one coin at random, replace it, and then choose a second coin. So we want the probability that you first choose a nickel and then a penny. So first off, independent or dependent? Well, if you're replacing the coin, you're basically resetting the experiment when you choose that second coin. So that means that the results of the first choosing will not affect the results of the second choosing. So these are going to be independent events, and we can just figure out their individual probabilities and multiply them together. So let's find out the probability now of that first event. And in general, we're doing a nickel followed by a penny. So independent, nickel followed by a penny. For a nickel, well, before we can figure out the probability of picking a nickel, we need to figure out the total possible outcomes. So adding all these together, we have 6 plus 5, that's 11, plus 3 is 14, plus 5 is 19, plus 2 is 21. So we have 21 overall possibilities of coins that we could get. And out of those 21, it looks like 5 are nickels. So 5 out of 21 is our nickel probability. Now for a penny, again, you have 21 possible outcomes because you replaced that coin that you just took out, that nickel you just took out, you put back. So still have 21, and we're multiplying these fractions now. But how about the numerator on this one? It looks like we've got 6 pennies. So 6 out of 21 is our penny probability. And now I just have to multiply these out. I'm going to reduce it a little bit before I do, though. So the 6 and the 21, I can reduce that to be, let's see here, reducing by 3s, we've got 2 over 7. And now multiplying, we've got 5 times 2 is 10. 21 times 7, that's going to be 147. So there's our probability. For this part of the problem, we're choosing one coin at random, not replacing it, and choosing another coin. So because we're not putting the coin back, what we pick on the first event here is going to affect what we can choose the second time around. So these events are going to be dependent. And now we want the probability that we choose a quarter followed by another quarter. So quarter, quarter. All right, probability of the first quarter. Now again, you might remember from part A of this question that we had 21 coins overall, so that's our denominator still, at least when we start off. And for quarters, they said we have 5 of those. So 5 over 21 is the probability of that first quarter. Now for the second quarter, in general, because you have taken a coin out of your bag there and not replaced it, you don't have 21 coins in there anymore. You've got 20 coins. You just lost a coin. And furthermore, the coin that you took out this first time around was a quarter. So that means you no longer have 5 quarters. Now you have 4 quarters that you could choose from. So let's go ahead and reduce this before we multiply. 4 over 20, we can actually let's do 5 over 20, even better. So that reduces to 1 over 4, and then this 4 and this 4 can cancel. So that leaves us with 1 in the numerator and 21 in the denominator. For this problem, I need to figure out whether the events are independent or dependent and then find the probability. So for both of these problems I'm considering, we have a shuffled set of 52 playing cards. First part of this question, we're choosing a card at random, replacing it, and then making another selection from that deck. So before we talk about the probability, is this independent or dependent? Well, since we are replacing the card, putting it back, that means that the second choosing here doesn't have anything to do with the first choosing. Whatever you choose that first time around, since you're just basically resetting the deck, you're not affecting the outcome of the second event. So that means these are independent of each other. They really have nothing to do with each other. For all intents and purposes, they're almost different problems. Now, finding the probability that we choose a diamond followed by a face card, so diamond, comma, face card. Let's get the diamond probability first. Then we'll find the face probability, and then we'll multiply those together. So for diamonds, the total possible outcomes for that one is going to just be the number of cards in our deck, which is 52 to start with. And then how many diamonds are in a deck? Well, a quarter of the deck is diamonds, so that's 13 of the 52 that are diamonds. You've got ace through 10, and then the 3 face cards. So now for face cards, speaking of face cards, in general now, again, we've got the whole deck for the total possible outcomes. And out of those 52 cards, how many are face cards? So that's going to be jacks, queens, and kings. So we have a jack, a queen, and a king for each of the 4 suits. That's a total of 12 face cards. Before we actually multiply these out, let's go ahead and reduce things a little bit. 13 over 52, for example, can reduce to 1 over 4. And there's a few ways I could go from here, but I'm going to do 12 over 4. That's the easiest thing to do. And that reduces to be 3 over 1. And taking a look at what's left now, we have a 3 in the numerator, just a 52 in the denominator, so 3 over 52. For this part of the problem, we still have our 52 playing cards, picking one at random, but now we're not putting it back. So now these events are going to be dependent on each other, because what you pick that first time around, since you're not putting it back, that affects what you can get the second time around, or at least the number of cards that you're choosing it from. So the probabilities are going to be different than they would have been. So let's find the probability now of choosing a non-face card followed by a queen. So the probability of a non-face card, we're starting with the 52 cards for the total possibilities. And desired outcomes, well, non-face cards is basically everything except for the jacks, queens, and kings. So that leaves the ace, the 2, and all the other number cards up to 10. That's a total of 10 cards in each suit that are non-face cards. And there's 4 suits, so that's 40 non-face cards overall. Now we're going to multiply that by the probability of picking a queen, given that we've already picked a non-face card. So let's talk about the total possibilities first. Since you already chose one of your 52 cards and didn't put it back, logically that means you have 1 less card. So 51 cards is what you have to choose from now. And how many queens are there in that 51 cards if you've already chosen a non-face card? Well, the queen is a face card. You picked something that was not a face card. So that means there's no way that you picked the queen. That means that all 4 queens are still remaining in the deck. All right, so now we can multiply these together. I'm going to go ahead and reduce things a little bit before I do that, though. So 40 over 52, I can reduce that by 4s to get 10 over 13. And then multiplying across in the numerator, I've got 40. And in the denominator, 13 times 51, I might be able to do this one mentally. So 10 times 51 is 510. 3 times 51 is 153. 510 plus 153, that's 663. There we go. You could verify it with a calculator, though. So there's our probability. For this set of problems, we want to determine whether our events are disjoint, also known as mutually exclusive, or overlapping, and then find the probability. So first situation here, we choose a card from a standard deck of 52 cards, and this will be the situation throughout, and then we want to know what is the probability that our card is a jack or an ace. Now, since we're dealing with or, that means we're going to have to add some probabilities together, but we might also need to subtract some overlapping probabilities. So we need to see if this is disjoint or overlapping. Now, the question then is, are there any jacks that are also aces? Are there any cards that belong to both of these categories? And there are not. A jack and an ace, those are completely different types of cards. There's no overlap. So these are mutually exclusive or disjoint. So to find the probability, let's start with the total number of cards, and we'll find the probability of a jack first. So this is out of 52 cards for the probability of a jack. And there are 4 jacks in a deck of cards, so 4 out of 52. Now for aces, there's also 4 aces in a whole deck of cards, so we're going to be adding another 4 out of 52. And again, there's no overlap between these groups, so we don't have to worry about subtracting anything that's in both groups. So adding these up then, that's going to be 8 over 52, which reduces to 2 over 13. For this problem, we want to figure out, first off, if I'm choosing a 7 or a club, is this disjoint or overlapping? Are there any 7s that are also clubs? There are. How about the 7 of clubs, right? So this is an overlapping set of things that we're choosing between. So when we find our probability, we're going to have to find the probability of a 7 and a club and add those, but then we're going to have to subtract the probability of things that are in both of these categories. So let's start with probability of a 7. In general, you've got 52 cards. That's your sample space here. And out of those 52, how many 7s do we have? Well, there's 4 7s in a deck of cards. There's 4 of every number, right? So 4 out of 52 is that probability. Now for clubs, how many of those are in a deck of cards? Well, a quarter of the deck is clubs, so that's going to be 13 that we're adding there. And now, how many cards are both clubs and 7s? Well, again, there's only one that's both of those. It's the 7 of clubs, so that's 1 out of your 52. We're going to have to subtract that because otherwise we're going to be counting it twice for both of these groups. So now adding all this together, we've got 4 plus 13 is 17, minus 1 is 16 out of 52, which we can reduce to 4/13. On this problem, we're asking about the probability that our card is red or evenly numbered. Now, before we actually do that probability, is there overlap or are these disjoint? Are there red cards that are even? Well, yeah, the 2 of diamonds and many others. So because we have overlap, we're going to find the individual probabilities and add them together, but then we're going to have to subtract the overlap. So let's do our probabilities now. So for the red, how many red cards are in a deck of cards? Well, we'll figure that out in a sec, but our total possibilities are 52, right? But now the possibilities that are actually red, the desirable outcomes there, half the deck is red. So for red by itself, we've got 26 out of 52. Now how about evenly numbered? Well, let's see here. We've got 4 of each number, and the numbers that are even, we've got 2, 4, 6, 8, and 10. There are 5 evenly numbered types of cards, and there's 4 of each of those because of the 4 suits. So 5 times 4, that's 20 evenly numbered cards overall in a deck of cards. Now here comes the tricky part, because there are some red cards that are also evenly numbered, and right now if we just add these the way they are, we're counting them both times, double counting them. So how many red cards are evenly numbered? Well, those would be the diamonds and the hearts. So we have the 2, 4, 6, 8, and 10 of diamonds and hearts. That's a total of 10 cards. That's half of these 20 here. So we're going to have to subtract 10 out of 52. So putting this together, 26 plus 20 is 46, minus 10 is 36 out of 52. Reducing that by 4, we get 9/13. For this last one, we're asking about the probability that a card is a black 9 or a spade face card. First off, are these disjoint or overlapping? Well, some black cards are spades. However, there are no 9s of any color that are face cards. A 9 is not a jack, a queen, or a king. So these are disjoint groups, which means we can find the probabilities individually and just add them together without worrying about any kind of overlap. So probability of a black 9, well, overall we've got 52 cards, and out of those 52, the only black 9s are the 9 of clubs and the 9 of spades, so that's 2 of them. For spade face cards, we have the jack, queen, and king of spades, so that's 3 of those. And then just adding those together, we have 5 over 52.